I am Paolo Dell'Aversana, Senior Geophysicist at NSPA, Upstream and Technical Services. Today I'm going to talk about a new methodology combining machine learning and musical attributes for seismic facies classification. Before starting, I would like to thank my colleagues and co-authors Alfonso Amendola, Gianluca Gabriellini, and Alfonso Junio Marini. This is the summary and few keywords of my lecture. I will introduce an hybrid approach of automatic classification and interpretation of geophysical data based on machine learning and digital music technology. This is the outline of my lecture. After a brief introduction, I will explain the basics of our methodology. Then I will show you several examples at an increasing level of complexity, and finally we'll conclude. There are several key problems in geophysics. Some of them are still unsolved, especially in complex geological settings, such as seismic facies classification, in particular distinction of high from low gas saturated reservoirs. And in general, sometimes it is very difficult to have accurate soil geometry definition and good imaging in difficult areas. I would like to propose in this lecture some special solutions and new methodologies for approaching these very difficult problems. Our methodology basically combines two different technologies. One is borrowed from industrial methods and applications of digital music, and these technologies are combined with modern machine learning algorithms. So basically we start from conventional geophysical data. Let's suppose that we have a seismic data set. So we start from conventional SegWi seismic formats, and we transform these SegWi formats into musical formats. For instance, we use MIDI format. MIDI is a typical protocol, standard protocol that is used in the industry of digital music. It means musical instrument digital interface. Then we extract MIDI features from our MIDI file, and we use these MIDI features as complementary attributes for data classification using machine learning algorithms. I need to explain to you what I mean by MIDI features. So this is a typical example of a MIDI file display. On the vertical axis we have the pitch. So basically we have a sort of virtual keyboard, and we are representing the pitch on this vertical axis. The pitch, you know, is related with instantaneous frequency. And on horizontal axis we have the time. This MIDI file, this simple display of a MIDI file, is a representation, a special representation of a small segment of a seismic trace that was converted from SegWi to MIDI format. In colors you have the MIDI nodes, so every small pixel of this display represents a musical MIDI node. So in this display we are representing a small segment of a seismic trace in terms of musical file. We can extract attributes from this type of file. So a MIDI feature is just an attribute that is extracted from a MIDI file like this. I'm talking about, for instance, the pitch that is related to instantaneous frequency. I'm talking about MIDI velocity, that is another attribute that is related to signal amplitude, or I'm talking about patterns and ensembles of MIDI notes. So I mean melodic, harmonic, rhythmic trends. These are all important information that can be extracted in terms of musical notes from our converted seismic data. Our key idea is that these types of MIDI attributes can be complementary to the traditional seismic features in order to characterize our seismic data and in order to classify them in some way. There are many benefits when we have MIDI files. I'm going to explain what are the main benefits. Basically, using MIDI files we can perform very accurate and fast big data mining, pattern recognition, data clustering, automatic classification. There are many applications in the musical domain, and we just want to transfer these applications and these algorithms from the musical domain to the geophysical domain after converting properly the seismic data, the geophysical data, into musical data. So let me explain what are the benefits of such transformation from seismic domain, geophysical domain, to the musical domain. MIDI formats require very low computer memory, so it allows fast data processing, fast application of advanced musical technologies for analysis and automatic classification. Furthermore, MIDI formats allow listening to the data, so we can add a new perceptive dimension in our interpretation, in our analysis. There are many applications, for instance, robust automatic classification using machine learning algorithms. Let me explain how do we move from SegWide to MIDI. I will go quite quickly in this part of the presentation because we presented many papers, we published many papers. One of them is this one that you can find on geophysical prospecting, where you can find all the mathematical and physical details of our transformation from SegWide to MIDI. I want to explain just the basic of our transformation in sounds coming from seismic data. First, we create spectrograms from seismic traces using different types of mathematical transforms like wavelet transform, Stockwell transform, or other mathematical formulas. Then, after obtaining the spectrograms from our seismic data, we transform the typical spectrogram attributes like instantaneous frequency, amplitudes, into sound attributes like pitch, sound intensity, note duration, and so on. In this figure, you can understand the conceptual scheme of our workflow. We have a seismic trace, its 3D spectrogram, and from the spectrogram, we can extract musical notes. So that for every seismic trace, I would say for every small piece of a seismic trace, we can get the spectrogram, and from the spectrogram, we can get the MIDI file, and we can listen to it. These are just the basic formulas that we use for moving from seismic traces to the spectrogram. In this case, I'm showing you the Stockwell transform. And the second formula shows you the relationship between the instantaneous frequency f with the ID MIDI note number n. It is a very simple nonlinear relationship. Now I would like to show you several examples at an increasing level of complexity. Let's start with a very simple case. I want to show you an example of a binary classification test in which we distinguish between low and high gas saturated sands through a trace-by-trace analysis and using MIDI attributes. So the geophysical problem is very complex. Sometimes it is very difficult or still impossible to distinguish high from low gas saturation just using instantaneous spectral attributes. Let me show you this example. This is a seismic trace in the top panel, and you can see two vertical bars, the red one and the green one. The green vertical bar show you a reservoir with a low gas saturation, and the other bar, the green one, show you a high saturation reservoir. The panel below, the bottom panel, represents the spectrogram obtained by this seismic trace. You can see in this case that the main anomaly and the main reflection events are in correspondence of the low saturation reservoir. That could be quite strange with respect to the high saturation reservoir. If we move few traces ahead, just let's say 100 meters on the lateral position, we get the opposite situation. So the main anomaly now is in correspondence of the high saturation level, and the lower anomaly on both seismic trace and its spectrogram is located in the low saturation. So looking at these two different traces, you can understand that it is very difficult or impossible to distinguish between low saturation and high saturation just using seismic traces or their instantaneous frequency properties. For that reason, we try to use our workflow. In this case, we start with seismic traces in SegWi formats. We transform that traces into MIDI format so that we have a MIDI file database coming from our seismic SegWi database. Then we use all the MIDI data. We try to extract features, MIDI features, from this data, like pitch, velocity, melodic trends, rhythmic trends, and so on. Then we apply a machine learning approach. The first step of a machine learning approach is to train the data. In this case, we are going to use a supervised machine learning approach strongly based on neural networks. So we trained a part of this data. We used a labeled data set for training our classifier. And after doing that training, we optimized our neural network classifier. And then we applied it to all the MIDI data sets for performing our automatic classification. And the final result was a binary split of our MIDI data into high saturation and low saturation categories. So the first step was importing data into the digital music domain after converting them from SegWi to MIDI. This is a typical digital music domain where you can see your MIDI files in terms of a MIDI display. You can visualize your MIDI attributes, you can mix them, you can do a lot of processing on these MIDI files that were originally seismic traces. Don't forget that. And this is the previous example that I showed you before. And here you have the seismic trace, and in the bottom panel you have the MIDI file display. Again, you have the pitch on the vertical axis and the travel times on the horizontal axis. We can play this file, so we can listen to it because it is a MIDI file, and we can play it very slowly using our musical software. So we can capture every single pattern of MIDI notes going very slowly from left to right in this seismic trace that was transformed into a MIDI file. This is the same seismic trace in the top panel, but in the bottom panel now we have the so-called pitch histogram, where the colors represent the histograms of the different individual musical notes. So you have basically a sort of spectral decomposition represented into the musical domain in terms of MIDI notes, each one characterized by its own color. And we can filter this data very easily, very quickly, immediately. For instance, this is a low pass filtered pitch histogram where we highlight the low frequency component. In particular, in this case, you can see that the high saturation level is very well highlighted on the right side of the slide. After working on our MIDI data in the musical domain, the next step is to import the MIDI files into the machine learning domain. Machine learning is a very important subfield of computer science that gives computers the ability to learn without being explicitly programmed. This is an important definition provided by Arthur Samuel. In other words, we provide computers with a set of labeled data that we use as a training data set from which a general inference, let's say a model, can be extracted. And this model can be a classification rule. Today, this approach based on machine learning is widely applied in the musical domain. For instance, we use it for musical genre classification, for song recognition from large database, from internet, something like Shazam, for instance. We just imported the same machine learning musical approach into the geophysical domain, applying these approaches, strongly based on neural networks and so on, to our seismic data transformed into musical data. For instance, this is an example of recording MIDI segments extracted from SegWi file. Let me zoom in this area. For instance, you can see here that every small segment of the seismic traces is transformed into a correspondent MIDI segment that is the target, one of the target of our classification. So we do that for all the small pieces, all the small segments of our seismic traces, trace by trace on the entire seismic dataset, and we create a MIDI dataset for classification. This is an example of features that we extract from our MIDI segments. For instance, rhythmic variability is an important feature, or beat histogram, maximum note duration, pitch histograms. There are many attributes, MIDI attributes, that have a strong link with the original seismic data and that we can use in our machine learning musical approach. Here in this panel, we are just setting the neural network parameters. We are optimizing the parameters of our classifier, going through the training on our training dataset. And finally, okay, these are just examples of values of our attributes. Finally, we have our classification. So this is just an example of our final classification, just a small part where every single piece, every single segment of our MIDI files is classified in our binary classification in this example. For instance, the trace number 257 is classified as a high saturation part of our database. So it belongs to the category of high saturation with a classification score of 0.6 and so on. The other example, in this case, the trace number 276 is classified again as a high saturation trace, but with a different classification score. We do that for all the small segments of our seismic data transformed into MIDI segments. And finally, we have our binary classification. This is just an example. So you can see here the classification results for a few samples for the lower layer in the upper panel and for the upper layer in the lower panel. You can see that this is a binary classification. So we have quite good split between high saturation and low saturation for the lower layer, and a better split for the upper layer. Of course, we never say yes and no. Yes, this trace belongs to high saturation category. Yes, this trace belongs to the low saturation category. We just assign a score, a classification score ranging from 0 to 1 to each element of our dataset. In this case, you can see that for the lower layer, there is an ambiguous area marked by the circle. So we changed a little bit our parameters of the neural network. We added also some additional musical attribute, and we improved our binary classification, like in this example here. You can see that for both layers, we have a good binary split between high saturation and low saturation categories. In this case, we obtained this very good result using a rhythmic musical attribute. So we try to use the rhythmic information included in the originally geophysical data for classifying them. This is very new in the geophysical world. We are using rhythmic, melodic, harmonic features included implicitly in our seismic data for classifying them using a machine learning algorithm. Just to explain the sense of these rhythmic attributes, you can see in this slide, looking at the pitch histogram, for the two different layers, for the low saturated layer and the high saturated layer, that we have effectively different rhythmic properties in the musical pitch. They are very different from a rhythmic point of view. I mean, the trend of each musical note in the two different layers. So these trends are very different, and this is the reason why rhythmic attributes or melodic attributes or other patterns of MIDI notes can be very diagnostic for distinguishing low saturation from high saturation. And this approach is completely new in geophysics. Here you can see a different representation of the rhythmic attribute that we use in this classification. For the upper reservoir and for the lower reservoir, you can see that the rhythmic attributes are significantly different. Example number 2, a little bit more complex. This is a multi-class classification test. Again, we try to classify different seismic phases, trace by trace analysis. Here we have several gas-filled channels that I labeled here as A, B, C, and D. We used the same approach that I explained to you before for distinguishing and classifying automatically by neural network the different gas-filled channels. For instance, if we focus our attention in this blue box, here you can see 4 seismic traces, 4 small segments of seismic traces crossing 2 of our channels, C and D. These 4 traces are very close to each other, about 12.5 meters in the lateral distance. And you can see that the channels C and D show very different pitches attributes that allow us to perform our classification, to distinguish the different channels. So at the end of the day, after applying our machine learning approach, that is exactly the same that I explained to you before, based on rhythmic attributes, melodic attributes, pitch attributes, and so on, we were able to classify the different channels in our section. Finally, the last example, we can enhance imaging using MIDI attributes. This is an example, a time slice extracted from a big 3D dataset. On the left panel, we have a typical seismic time slice. On the right side, we have an example of MIDI attribute. In this case, this attribute is based on note length. And you can see that we can still improve the imaging. For instance, let's focus our attention in this box. You can see that we can gain imaging quality using MIDI attributes. So let me conclude. We applied a new approach, an hybrid approach, I would say, combining machine learning and musical technology for classifying automatically our geophysical data. And the MIDI features that have no equivalent seismic attributes helped us significantly to process and to analyze and finally to classify our seismic data. Our approach is very fast and accurate at the same time because it works on MIDI files that require very small computer memory. Indeed, MIDI files occupy less than 1 kilobyte for each trace, and they are very, very light from a computer memory point of view. On the other side, they store all the most relevant physical properties of our original data. For that reason, MIDI files and machine learning techniques that use MIDI files can be applied to big data mining and to fast and accurate automatic analysis, pattern recognition, classification, and so on. There are also many other possible applications in different fields, in well logs, but also in biomedical data analysis, in analysis of financial trends, and so on. So these are the main references, including all the technical, mathematical, physical, geophysical details of this lecture. And thank you very much.